So if you take a grid of numbers, let's just say a 2 by 2 matrix, right? You've got a 0 and a -1 on the top row, and a 1 and a 0 on the bottom row. And you take that entire grid and you put it into an exponent.
Which just looks wrong.
It looks like a typo. Like, it
Yeah.
looks like complete mathematical nonsense. I mean, if you write down the letter E, the constant number, around 2.718, and you literally raise it to the power of a box of 4 separate numbers, the average person is going to look at that and say, well, you can't do that.
Right, yeah.
You can't multiply a number by itself a grid amount of times. It just doesn't make sense.
It definitely breaks the brain a little bit, especially if you're only used to standard high school algebra. The immediate instinct is to just reject it entirely.
Right. But here is where it gets incredibly cool. Because not only is it mathematically valid, but it's actually the exact same mechanism used by physicists to, understand the universe in quantum mechanics.
Yeah, which is huge.
And remarkably, it is the exact math currently running live in a web browser for a very specific group of listeners joining us today.
Which is such a fascinating convergence of disciplines, honestly. You
Yeah.
have this really abstract theoretical mathematics just directly colliding with cutting-edge front-end web development.
Exactly. And that brings us to our mission for today's deep dive. I really want to send a massive, highly specific welcome to you, the Bus and Sigma Scholars of Edward Little High.
Welcome, scholars.
You are essentially the third person in the room with us today. We know you have just conquered this really fascinating exercise. Like, you've built a toy model using the Comic Graphics library, and it maps the turbulent, tragic romance of Romeo and Juliet to a matrix exponentiation differential equation.
Which is no small feat. Taking abstract mathematical concepts, and especially differential equations, and then forcing them to manifest visually as a working interactive simulation in a browser. That is an exceptional achievement.
Definitely.
It requires a lot of different conceptual muscles working together at the exact same time.
Okay, so let's unpack this. Our goal today is twofold. First, we are going to look under the hood of your current Romeo and Juliet toy model. We need to explore how this is actually working.
Right.
And I don't just mean the math part of it. We need to talk about the literal web architecture that is physically running your code, because running Python in a browser is, well, historically, it's notoriously difficult.
Oh, incredibly difficult.
And then after that, we need to completely demystify that matrix exponent.
And once we establish that foundation, we're going to fulfill your specific request, because you've mastered the current simulation and you need a follow-up matrix exponentiation model.
The next challenge.
Exactly. So we're going to advise you on that next challenge, one that introduces a completely different, frankly explosive dynamic between our star-crossed lovers. And ultimately, we're going to connect your specific code to Schrodinger's equation.
So let's just start with the literal engine calculating your code. You, the scholars, are writing and running Python inside a web tab. To someone who isn't, steeped in web development history, that might not sound like a huge deal.
Right, because we run complex stuff in browsers every day.
Yeah, exactly. But historically, getting Python to run locally in a web browser is a massive technical hurdle. Why is that so hard?
Well, what's fascinating here is sort of the rigid biological reality of the web, so to speak. Browsers were built with a very specific, natively understood language, and that language is JavaScript.
Okay.
From the early days of the internet, if you wanted a browser to do literally anything interactive, click a button, move an image, validate a form, you had to write it in JavaScript. The browser contains a JavaScript engine like V8 in Chrome, for example.
Right.
And that engine compiles and executes that JavaScript code on the fly.
So JavaScript is the native tongue. It's basically what the browser's brain is naturally wired to understand.
Precisely. Python, on the other hand, is a completely different language. It has a completely different runtime environment, typically written in C, which we call CPython.
Okay.
So if you just hand a browser a Python file, it stares at it blankly. It has absolutely no idea what to do with a def keyword or an import statement.
It's like handing a menu in Russian to someone who only speaks Spanish.
Exactly. So for decades, if educators or developers wanted to run Python code on a web page, say, for an introductory computer science course like the one you're taking, they had to rely on some pretty clunky workarounds.
And looking at the provided sources, it seems like the most common workaround historically was what we call server-based execution. Platforms like Replit or Python Tutor use this for a long time. How exactly does that bypass the language barrier?
It bypasses the browser by just, well, not using the browser's brain at all.
Oh.
Yeah. In a server-based model, the web page is essentially just a dumb terminal. It's a text box. You type your Python code into that box, and when you hit Run, the browser bundles up the text you just wrote and sends it as a data packet over the internet.
To a server somewhere.
Right, to a remote server sitting in a data center. And that remote server has standard Python installed on it.
So the server is doing all the actual heavy lifting.
Yes. The remote server runs the code, figures out what the output should be like, maybe it's a print statement or an error message, and then it sends that result back across the internet to your browser, which finally displays it on your screen.
Okay, I can see how that works for a simple script that just prints hello world.
Right.
But that sounds like an absolute nightmare if you want to build what the scholars are building.
Yeah.
A highly interactive 30 frame per second graphical animation.
It is entirely unfeasible for interactive graphics.
I would imagine.
Think about it. If you are tracking the X and Y coordinates of a mouse cursor to update Romeo and Juliet's love levels in real time, you cannot afford to send that data back and forth to a server hundreds of miles away 30 times a second.
The lag would be
A
terrible.
latency, the delay caused by the literal speed of light and network routing it, would make the animation incredibly choppy. Plus, it completely falls apart if your internet connection drops for even a second.
Right.
And just from an administrative standpoint, paying for the server compute time to run thousands of students' continuous while loops, that gets very expensive very fast.
So if sending it to a remote server is out, what was the next option? Because the sources mentioned something called transpilation. And I know tools like Brython and even older versions of the CMU CS Academy platform relied on this.
Yeah, so if you can't send the Python away and the browser only speaks JavaScript, the logical alternative is translation. Translation is basically a portmanteau of translation and compilation. A program reads your Python code and literally rewrites it line by line into functionally equivalent JavaScript code.
It just translates it into the browser's native tongue on the fly.
Exactly. Then the browser just runs the generated JavaScript. And that solves the latency issue because everything runs locally on your machine. No server required.
But the sources highlight a fatal flaw with this transpilation method, specifically something they call the main thread blocking problem. And this seems to be the crux of why your current setup is so revolutionary. What does it mean to block the main thread in a browser?
This raises an important question about how browsers are fundamentally architected. A browser tab typically operates on a single main thread.
Just one.
Just one. You can think of a thread as a worker who can only do one task at a time. And this single worker is responsible for everything you see and do on that page.
Everything.
Everything. They have to draw the pixels on the screen, they have to listen for you clicking the mouse or pressing a key, and they have to execute any JavaScript code.
So this one worker is essentially running around frantically trying to do all the chores in the house simultaneously.
That's a really good way to look at it. And because there is only one worker, JavaScript was specifically designed to be asynchronous and event-driven. It doesn't like to wait.
What do you mean by that?
Well, if a JavaScript program says wait for the user to click a button, the worker doesn't literally freeze in place and stand there waiting. It sets a reminder to check back later and then goes off to draw the next frame of the web page.
But Python isn't built like that, is it?
No, it is not. Python is traditionally synchronous. If you write a standard Python while true loop, or if you use the native input function that asks the user to type something, Python literally stops and waits.
It expects the whole world to pause.
Exactly. It expects the entire program execution to freeze until that input is received.
So wait, what happens if you transpile a synchronous Python while loop into JavaScript and then force that single web browser worker to run it?
The worker gets trapped. It enters the infinite loop and can never leave to do its other chores. It stops updating the screen. It stops listening to your mouse clicks.
So the whole thing just crashes.
The entire browser tab freezes, becomes completely unresponsive, and eventually the browser throws an error asking if you want to force quit the page. This is the main thread blocking problem.
Wow. This sounds like a fundamental incompatibility. I mean, trying to run native Python behavior in a browser is like trying to run a diesel engine on unleaded gas.
Yeah, that's a good analogy.
The fundamental combustion mechanics are just completely different. The server model is like building a remote diesel engine and remote controlling it. And transpilation is like building a complex adapter that tries to convert diesel to unleaded on the fly, but it eventually floods the engine and stalls the car.
I really like that analogy, and that brings us to the breakthrough that is actually powering the Scholar's toy model right now. IO-did-U and WebAssembly.
So how does WebAssembly fix this? Is it just like a better translator?
It's not a translator at all, actually. It's an entirely new paradigm. WebAssembly, which is often abbreviated as WASM, is a low-level bytecode instruction set.
Bytecode.
Yeah. Without getting too deep into the weeds here, over the last few years, all the major browser manufacturers agreed to build a second engine inside the browser alongside the JavaScript engine.
Okay, a second engine.
And this new engine doesn't read human-readable code. It reads raw, binary instructions bytecode and executes them at near-native speeds.
Meaning it runs almost as fast as if you had installed the program directly on your Windows or Mac operating system.
Precisely. So because of WebAssembly, we don't have to translate Python into JavaScript anymore. Instead, the developers of a project called Pyodide took the actual original CPython runtime, the core C program that understands and executes Python code, and they compiled that entire C program into WebAssembly.
Wait, they put the literal Python engine inside the browser.
Yes. When you load your Romeo and Juliet app, your browser downloads a compiled version of the Python runtime itself. So your browser isn't translating your Python code. It is genuinely running Python locally, entirely inside your machine's memory without ever needing a remote server.
That is incredible. But I'm going to push back here for a second.
Sure.
Because if WebAssembly is running the actual CPython runtime, doesn't it still suffer from that blocking problem? I mean, if I write a while true loop in Python, and the native Python engine is running in WebAssembly on the browser's main thread, won't it still trap that single worker and freeze the tab?
You've hit on the exact reason why standard Pyodide wasn't enough for educational platforms, and why the CMU team had to develop a custom solution called PyDU.
Okay.
You're absolutely correct. Standard WebAssembly is completely unblockable. If you ask it to pause for an input statement, it will freeze the main thread just as badly as transpiled JavaScript would.
So how do they get around it? Because the scholars are writing code that clearly pauses and animates smoothly without crashing their Chrome tabs. The source material mentions a custom trace function and something called unthrow. How does that actually work mechanically?
This is where we get into some truly brilliant computer science wizardry. To solve the blocking problem natively, the PyDU team had to figure out a way to pause Python, let the browser's main thread go do its chores like draw to the screen, and then resume Python exactly where it left off, all without Python ever realizing it was paused.
How do you pause something that is fundamentally designed to never pause?
They utilize a mechanism built into CPython called a trace function.
A trace function.
Yeah, usually trace functions are used by debuggers. They act like a watcher that executes a tiny bit of code before every single line of your Python program runs. PyDU basically injects a custom trace function into the runtime.
Okay, so this watcher is keeping an eye on the code line by line. What is it watching for?
It's watching for any event that would normally block the thread. For example, a call to a time delay, or an input prompt, or just the basic need to yield to the browser so it can draw the next frame of an animation at 30 frames per second.
Right, because it needs to draw.
When the watcher detects that a pause is necessary, it does something radical. It intentionally throws an exception. It crashes the execution.
Wait, it intentionally throws an error. Doesn't that just break the program entirely?
Normally, yes, it would be a fatal crash.
Hmm.
But they wrap your entire program execution in a massive, custom try-except block, which is powered by a C-level manipulation tool called unthrow.
Unthrow. Okay.
When the trace function throws this specific intentional exception, the unthrow tool catches it. But right before it completely terminates the run, it reaches into the computer's memory and rolls up the entire current stack frame.
When you say stack frame, what does that actually mean in plain English?
Think of it as a perfectly preserved snapshot of your program's brain at that exact millisecond. It saves every variable, every coordinate, exactly which line of code you were on, and the entire nested history of which functions, called which functions to get you there. It takes this entire snapshot and saves it in a safe place.
And then what? The program just stops.
Yes, the Python execution completely exits. And because it exits, control of the main thread is officially handed back to the browser.
Oh.
The browser's worker is suddenly free. It can now draw the updated schema graphics canvas. It can check if the user clicked the mouse. It can handle network requests.
Okay, but the student's program is dead in the water.
Only temporarily.
Ah.
Before exiting, the PyDU system registers a callback with the browser. It essentially says, hey, browser, when you are done drawing the screen or when the user finally presses a key, call me back.
And then?
When that event happens, the system takes that perfectly preserved snapshot of the stack frame and forcefully injects it back into the Python engine.
It just shoves it back in.
It rewrites the memory, reinstates the variables, and jumps the execution pointer right back to the exact line of code where it threw the exception.
That is mind-blowing. It's literally freezing time, letting the universe move forward, and then unfreezing time without the program ever knowing it was stopped. It just thinks it took a quick nap.
It is a remarkable piece of engineering. And according to the sources, this exact same stack frame saving mechanism is how they built the replay debugger mode.
Oh, because they're already saving the state?
Right? Because they can capture the state of the program at any moment. They can save the scope, the variables, and the visual output at the execution of every single line of your code, allowing you to scrub backward and forward through time to find bugs.
So when the scholars are writing their Romeo and Juliet simulation, they are benefiting from an incredibly complex dance between WebAssembly, C-level memory manipulation, and intentional exceptions, all just to make Python play nice in a browser tab.
Precisely.
But with all this power comes responsibility, right?
Right.
Because the PyDo engine is so specifically engineered to yield to the browser's drawing cycle, it relies on the programmer following a very strict set of rules. And that brings us to the architecture of their code, MVC.
Right. Model View Controller. If you look at the CMU graphics guide provided in the sources, it makes it very clear that your code must be built on this paradigm.
It's mandatory.
It's not just a polite suggestion for clean code. It is the fundamental law of physics in their CPCS programming mode.
If we step back for a second, what exactly is the philosophy behind MVC? Why do we need it?
If we connect this to the bigger picture of software engineering, MVC is a strategy for separating concerns. When you build a complex application, things get incredibly messy if the code that calculates the math is tangled up with the code that draws the shapes on the screen.
Spaghetti code.
Exactly. MVC demands that you split your program into 3 distinct tilos.
The model, the view, and the controller. Let's break those down as they relate specifically to the scholars' Romeo and Juliet code. Let's start with the model. The sources state that the model is where all the data lives, specifically inside something called the app object.
Yes. The app object is a predefined container representing the current state of your application. When you write your onApp_start_app function, you are defining the model.
You're setting the baseline.
You create variables like app.x to represent Juliet's love level and app.y for Romeo's love level. You also have built-in data like app.width and app.height, which define the canvas size, and app.steps/second, which dictates the frame rate.
So the model is just raw numbers.
Yeah.
If I only had a model and I ran the code, I would just see a blank white screen, right?
Correct. The model has no visual representation whatsoever. It is pure data. To see anything, you need the view.
In CMU graphics, the view is the redraw app function. And the cardinal rule here is that the view's only job is to draw.
That's it.
It looks at the raw numbers in the app object, and it uses drawing functions like drawRect, drawCircle, and drawLine to create a visual representation of those numbers.
And here is a crucial detail about the view in this specific framework.
Yeah.
You, the programmer, never call redraw directly. You never write redraw in your code to trigger it. The underlying PyDo engine calls it automatically, based on that app.steps/second timer we mentioned earlier.
So if it's running at 30 frames per second, the engine is secretly calling redraw 30 times every second.
Right behind the scenes.
And the sources point out something really interesting about how it draws. It doesn't just move shapes around. On every single call, it completely clears the entire canvas, wipes it blank, and redraws every single element from scratch.
Yes, exactly.
You never manually erase a circle to move it. You just let the engine wipe the board and draw a new circle in the new location.
Which is why the view must be completely passive. It cannot change the data. If you try to update Romeo's love level inside redraw by writing, say, app.y, app.y+1, you're creating a feedback loop that will break the system. The view is strictly read-only.
Okay, so if the view can only read the data and the model just stores the data, how does the data ever change? How does the animation actually move?
That is the sole responsibility of the controllers. These are your event functions, like onMousePress, onFeedPress, and most importantly for a physics simulation, onStepApp.
And just like the view, you never call the controllers directly. The PyDo engine sits there listening for events. When it detects a timer tick, it triggers onStep. And inside onStep, you are finally allowed to change the math. You update app.x and app.y.
The stakes here are absolute. The CMU guide is explicit about what they call MVC violations.
That sounds serious.
If you break these rules, for example, if you try to put a drawCircle command inside your onMousePress controller, or if you try to mutate a variable inside your redraw view, your program doesn't just act glitchy.
What happens?
The PyDo engine is actively monitoring for these violations, and it will throw a runtime error and crash your program instantly.
Wow. So controllers change the math. The view draws the math, the model holds the math. It's a perfectly balanced triangle. And in your current Romeo and Juliet code, your main controller is onStep. Every time the clock ticks, OnStep looks at Romeo and Juliet's current love levels, calculates the tiny rate of change based on their current feelings, and nudges their values forward by a tiny fraction of a second.
It is a manual, iterative, frame-by-frame update.
Which is perfectly fine for a simple visual simulation. It's a method called numerical integration, specifically the Euler method. You approximate the curve by taking tiny linear steps.
But the whole point of our deep dive today is that there is a better way. Mathematically speaking, if you don't want to calculate all those tiny error-prone steps,
Yeah.
if you want to jump perfectly from time zero directly to time t in the future,
Yeah.
you need the exact analytical solution.
And that solution brings us to the mysterious operation we teased at the very beginning, matrix exponentiation, written mathematically as e to the power of at.
This is where we have to fundamentally rewire our understanding of basic arithmetic. When you first encounter e to the at, where a is a matrix, the first instinct is to apply what you know about regular exponents.
Right. If I see 5 squared, I know that means 5 times 5. If I see 2 cubed, it's 2 times 2 times 2. So if I see e raised to the power of a matrix, I want to multiply e by itself a matrix number of times.
Which is impossible.
Exactly. But as we established, that is complete, utter nonsense. You cannot multiply a number by itself a grid amount of times.
So to understand what it actually means, we have to trace the concept back to its origins in one-dimensional calculus. We have to look at the simplest differential equation, a system where the rate of change of a value is directly proportional to the value itself.
Okay, let's ground that in reality. What is an example of a value that changes based on how much of the value is already there?
The most common example is compound interest in a bank account. The more money you have in the account, the more interest you earn,
Which adds to the total.
which makes you earn even more interest the next day. The growth rate is proportional to the current state. Another classic example is population growth in an environment with unlimited resources.
Like rabbits.
Like rabbits. The more rabbits you have, the more babies they have, which means even more rabbits reproducing. Or the early stages of an epidemic. The more people infected, the faster the disease spreads.
In all of these cases, the bigger the value gets, the faster it grows. It's a self-reinforcing feedback loop. And in calculus, the exact solution to the self-reinforcing growth equation involves the exponential function. The value at any given time t is equal to the initial starting value multiplied by e raised to the power of the growth rate times t.
Exactly. E to the RT. The reason the number Euler's number is so special in mathematics is because the derivative of e to the x is simply e to the x.
It doesn't change.
It is the only function that is its own derivative.
Yeah.
So it perfectly solves an equation where the rate of change needs to exactly equal the current state.
So, if we know that e to the RT works perfectly for a one-dimensional value, like a single bank account or a single rabbit population, how on earth do we bridge the gap to matrices? Because matrices represent multidimensional systems, like Romeo and Juliet acting simultaneously.
The bridge is one of the most beautiful concepts in mathematical analysis. The Taylor series. Centuries ago, mathematicians realized that you don't have to calculate complicated functions like sine, cosine, or exponents directly.
What do you do instead?
You can approximate any smooth function using a polynomial.
A polynomial.
Yeah, an infinitely long string of additions and multiplications.
Let's visualize this. What does the Taylor series for e to the power of some input look like?
The definition of e's raised to any input x can be rewritten as this infinite sum. It is 1 plus the input x plus the input squared divided by 2 factorial plus the input cubed divided by 3 factorial plus the input to the 4th power divided by 4 factorial, and so on, stretching out to infinity.
And for anyone who needs a quick refresher, a factorial written with an exclamation point just means multiplying the number by every whole number below it. So 3 factorial is 3 times 2 times 1, which is 6. 4 factorial is 4 times 3 times 2 times 1, which is 24.
Correct. And this is the profound breakthrough. Look closely at the operations in that infinite polynomial. We are doing addition, we are doing multiplication, raising the input to a power, and we are doing scalar division, dividing by those factorial numbers.
Okay, I see where this is going. Can you do those operations on a matrix?
Yes. As long as the matrix is square, like a 2 by 2 or a 3 by 3 grid, you can multiply it by itself to square it. You can multiply it again to cube it. You can divide all the numbers in the grid by a single scalar factorial, and you can add the resulting matrices together.
So we don't have to invent new math to put a matrix in an exponent. We just plug the matrix into the Taylor series.
Exactly.
The definition of e to the power of matrix A simply becomes the identity matrix, which is the matrix equivalent of the number 1 plus a squared over 2 factorial plus a cubed over 3 factorial out to infinity.
It is a stroke of absolute genius,
Yeah.
but it immediately raises a practical concern.
Yeah, no kidding. We are talking about infinite matrix multiplication and infinite matrix addition. If I type this into Python, how does the computer, or a human for that matter, ever calculate the final answer? Does the PyDiDU engine just sit there spinning its wheels until the end of time trying to reach infinity?
This is where those factorials in the denominator save the day. Think about how fast factorials grow. 5 factorial is 120. 10 factorial is over 3 million.
Wow.
20 factorial is a number so massive it's hard to even comprehend. As you move further down the infinite series, you are dividing your matrix by incredibly unfathomably large numbers.
So the terms become infinitesimally small. They essentially shrink to zero.
Precisely. The sum rapidly converges to a stable, finite matrix. The computer only has to calculate a handful of terms before the additions become so small they don't change the decimal values anymore. But what is truly magical is that in many practical systems like the Romeo and Juliet model, we don't even need the computer to calculate it.
I mean, the patterns, right?
Yes. Incredible algebraic patterns emerge that let us skip the infinite addition entirely and find an exact formula.
Let's prove that. Let's look at the specific matrix powering the scholar's current simulation. The rules of this Romeo and Juliet model are very specific. Juliet's rate of change is equal to negative Romeo.
Right. If Romeo's love is high, Juliet's rate of change is negative, she pulls away.
And Romeo's rate of change is equal to positive Juliet. If Juliet's love is high, Romeo's rate of change is positive. He chases her. So she flees and he pursues.
If we package their states into a vector, the matrix M that represents these rules of change has a top row of 0 and -1, a bottom row of 1 and 0.
Okay, so M is 0, -1, 1, 0. Let's see what happens when we plug this specific, deceptively simple matrix into our infinite Taylor series. First, we have the identity matrix, which we'll call I. Then we add our matrix M times T. So far, nothing special.
But then we need the next term in the polynomial, which involves squaring M. If I sit down with a pencil and manually perform matrix multiplication, multiplying that grid by itself, the zeros cancel things out, the negative ones flip things around, and the result is a matrix with -1 and 0 on top and 0 and -1 on the bottom.
Which is exactly the negative identity matrix, negative I.
Okay, what about the next term? We need to cube the matrix. M cubed is just M squared multiplied by M one more time. But we just proved that M squared is negative I. So M cubed is just negative I times M, which is simply negative M.
And let's do one more. To get M to the fourth, we multiply M cubed by M. That's negative M times M, which is negative M squared. And since M squared is negative I, we have negative I.
Which brings us right back to positive I, the original identity matrix.
This is incredible. It cycles perfectly. Every single time you multiply by the matrix, it steps through a 4-part loop. M, then negative I, then negative M, then back to I, over and over, infinitely down the polynomial.
And this cycling pattern allows us to organize the infinite chaos of the Taylor series into two very neat piles.
Piles.
Look at the powers of t in the series. All the even powers of t, like t squared, t to the fourth, t to the sixth, have an identity matrix attached to them, either positive or negative. And all the odd powers of t, like t to the first, t to the fifth, have the M matrix attached to them.
Let's look at what this actually builds inside the final grid. The identity matrix only has numbers on the main diagonal, the top left and bottom right. So if we group all the terms with the identity matrix, they all pile into those diagonal slots. For the top left entry, the infinite series becomes 1 minus t squared over 2 factorial plus t to the fourth over 4 factorial minus t to the sixth over 6 factorial, alternating plus and minus forever.
To a mathematician, that specific sequence of alternating even powers over factorials is as recognizable as a familiar face.
What is it?
It is the exact fundamental Taylor series definition for the trigonometric function cosine of t.
And if we look at the odd powers that land on the M matrix, they populate the off-diagonal slots, the top right and bottom left. For the bottom left entry, the series is t minus t cubed over 3 factorial plus t to the 5th over 5 factorial minus t to the 7th over 7 factorial.
And that sequence is the exact Taylor series for sine of t.
So through the sheer structural elegance of the math, the infinite polynomial collapses into a beautifully simple 2 by 2 matrix. Without taking infinite time, we know exactly what the series converges to. The top row becomes cosine of t and negative sine of t. The bottom row becomes sine of t and cosine of t.
Which is the standard formula for a perfect, flawless 2D rotation matrix.
If you multiply any coordinate by that matrix, it perfectly rotates that point around the origin by t radians. This absolutely blows my mind. You take a psychological relationship, one person chases, the other flees. You write down those local rules in a basic matrix. You shove that matrix into an infinite exponential polynomial, and out pops perfect circular geometry.
They are trapped in an endless, stable orbit of chasing and fleeing.
It's a profound geometric truth about differential equations. Let's think about why it forms a circle. The original matrix rules dictated that the velocity of Romeo and Juliet's love is always perfectly perpendicular to their current state.
Yes, if you are standing in a field and your instructions are to only ever take a step precisely 90 degrees away from the direction of the center of the field, what path will you walk?
You'll walk in a circle. It's the only way to continuously move perpendicular to your position without getting closer to or farther from the center.
Exactly. The matrix exponentiation simply takes that instantaneous local rule of being perpendicular and integrates it over time into a global trajectory, which is a rotation. The sources even give us a fantastic shorthand to conceptualize this, linking it to Euler's famous matrix identity.
Let's talk about that, because the source material brings up putting pi into the matrix. If you take our matrix and multiply it by pi, so we have negative pi and pi on the off diagonals, and you plug that into the exponent operation, what do you get?
Well, according to our formula, you are plugging pi into the sine and cosine functions. The cosine of pi, which is 180 degrees, is -1. The sine of pi is 0. So the resulting matrix has -1 on the main diagonals and 0 everywhere else.
Which is exactly the negative identity matrix, which perfectly aligns with geometry. If you rotate any point 180 degrees around an origin, it ends up exactly on the opposite side. You just multiply its coordinates by -1.
This is why physicists, engineers, and mathematicians rely so heavily on matrix exponents. It provides an unbreakable bridge between local rules of change, how Romeo reacts to Juliet at this exact microsecond, and global motions through time.
You don't have to calculate every frame.
Exactly. We can plug in tot equals 100 and jump perfectly analytically to their state 100 seconds in the future.
And having conquered that stable circular orbit, you, the Bus and Sigma scholars, are ready for the next level. You've mastered the stable loop, but differential equations can model systems far more complex and dangerous than just going in circles. You asked for advice on a follow-up model for your coding assignment, and the source material provides a brilliant, slightly terrifying alternative.
Indeed. We are going to look at what the source defines as the more Shakespearean model. In the first model, we had a classic pursuer-distancer dynamic. But let's change the rules of the differential equation. What if Juliet's rule is symmetric with Romeo's? What if they both feed off of each other's feelings?
So in this new model, Juliet's rate of change isn't negative Romeo anymore. Her rate of change is positive Romeo, and Romeo's rate of change is positive Juliet. If he loves her, that makes her love him more. And because she loves him more, that makes him love her even more. It's a pure, unadulterated feedback loop.
Mathematically, our fundamental matrix M changes. The negative sign disappears. The top row is now 0 and 1, and the bottom row is 1 and 0. It is a perfectly symmetric matrix across the main diagonal. And this seemingly tiny change, flipping one minus sign to a plus sign, completely destroys the stable geometry we just built.
If you exponentiate this new matrix, you don't get sines and cosines anymore.
No, you don't.
The infinite Taylor series doesn't alternate plus and minus, so it doesn't fold up into a neat little circle. It fundamentally changes the space. And I absolutely love how the source material explains visualizing this using vector fields. Can you break down what a vector field is visually?
Certainly. Imagine your CMU graphics canvas. Instead of just drawing a single dot representing Romeo and Juliet's current state, we want to see the underlying current of the math across the entire board. To do this, you go to every single point on your 2D grid, every possible combination of love and hate, and at that point, you evaluate the matrix multiplication M times V.
That multiplication gives you a velocity vector. It tells you which way and how fast the math wants to push you if you were standing on that exact pixel.
Exactly. You draw a little arrow at that pixel pointing in that direction. If you do this for a grid of points across the whole screen, You get a dense map of arrows that looks like a weather map showing wind currents.
In your original toy model, the pursuer-distancer one, those arrows formed a perfect whirlpool. It was a stable, circular current flowing around the origin. You drop a leaf into that mathematical river, and it just spins in a circle forever. But this new symmetric model, the flow field is radically different.
It creates what mathematicians call a saddle point. The mathematical current squishes inward along one diagonal axis and it stretches outward, accelerating infinitely along the other diagonal axis.
So returning to the river analogy, this new assignment isn't a calm whirlpool. It's a violent, diverging, rapid splitting around a massive rock. If Romeo and Juliet start anywhere in the upper right quadrant of the plane, meaning they have even the tiniest bit of initial positive feelings for each other, the current catches them. The mutual feedback loop takes over, and their feelings spiral out along that stretching diagonal towards infinity. It is an explosive, infinite surge of love.
However, the symmetry cuts both ways. If they start in the lower left quadrant, where negative feelings dominate, say, they remember they are Montagues and Capulets. The mathematical flow catches them and pushes them in the exact opposite direction.
Down the other side of the saddle.
The feedback loop amplifies their disgust, and their relationship plunges infinitely deep into hatred and feud.
It is the ultimate dramatic vector field. It perfectly models how a passionate relationship without any dampening mechanisms just explodes, for better or worse. But what is truly mind-bending and what elevates this entire deep dive to what I call the boss level is that this exact same mathematical structure, this exact same matrix exponentiation, scales up from a teenage romance simulation to describe the fundamental fabric of the universe itself.
This is why this math is so vital. We have to talk about Schrödinger's equation. When you study quantum mechanics, you are trying to predict how incredibly tiny things like electrons or photons change over time. Schrödinger's equation is the fundamental law governing that evolution. And while it looks intimidating, written on a chalkboard with Greek letters and partial derivatives, structurally, it is identical to your Romeo and Juliet system.
Let's break that connection down. In the CMU graphics model, we have a 2D vector, an x and a y, representing the state of Romeo and Juliet. What is the equivalent in Schrödinger's equation?
In quantum mechanics, instead of a simple two-dimensional vector, you have what's called a quantum state vector, often denoted by the Greek letter psi. This vector lives in a highly complex, sometimes infinite-dimensional space called a Hilbert space. But conceptually, it is just a list of numbers packaging together all the information about the quantum system, the probabilities of where a particle might be, its momentum, its spin.
Okay, so we have a massive state vector instead of a 2D state vector. What about the matrix? In our web code, we use a 2x2 matrix to dictate the rules of how the state changes.
In quantum mechanics, the rules of change are dictated by an operator called the Hamiltonian. You can think of the Hamiltonian as a massive, incredibly complex matrix that encodes the total energy of the system, all the kinetic energy of the particles moving, and all the potential energy of the forces acting on them. Schrödinger's equation simply states that the rate at which the quantum state vector changes over time is proportional to this Hamiltonian matrix acting on the state vector.
But if the Hamiltonian is just a matrix, and the quantum state is just a vector, and they feed back into each other, wouldn't the quantum universe just explode? Like, if the energy acts on the state and the state changes, wouldn't it just stretch out to infinity like our explosive, more Shakespearean model? Why doesn't every atom in the universe just instantly rip itself apart?
That is the crucial question, and the answer lies in one single, incredibly important symbol sitting right in the middle of Schrödinger's equation, the imaginary unit, I, the square root of -1.
Wait, how does an imaginary number prevent the universe from exploding, and how does it relate to our matrix math?
Because multiplying by I in the complex plane does a very specific geometric thing. If you take a complex number and multiply it by I, it rotates that number exactly 90 degrees around the origin. The imaginary unit I acts as a perfect rotation operator. It plays the exact same mechanical role as the matrix in your very first Tor model.
Oh, wow, let me make sure I'm getting this. The Hamiltonian matrix tells the quantum state how much to change based on the energy. But the imaginary I in the equation grabs that rate of change and twists it 90 degrees, forcing the velocity to be perfectly perpendicular to the current state.
Precisely. By ensuring that the rate of change is always orthogonal to the state itself, the I in Schrödinger's equation forces the quantum system to undergo continuous rotation. Instead of the state vector stretching out to infinity, it oscillates, it waves. This is the fundamental origin of the wave nature of quantum mechanics. It's an infinite dimensional rotation in a complex vector space.
That is honestly breathtaking. Without that rotational twist, without the exact same matrix math that powers a circular web animation, the quantum universe would just exponentially decay or explode. But because of it, the universe oscillates. Particles exist as stable probability waves. The math keeping a digital Romeo and Juliet in a stable orbit is the same math keeping the atoms in our bodies from tearing themselves apart.
It demonstrates the incredible unifying power of differential equations. The universe operates on rules of change, and matrix exponentiation is the language we use to translate local rules of change into global reality.
But recognizing the profound beauty of the math is only half the battle for the scholars. They have an assignment to finish. If they are going to actually build this new squish and stretch Shakespearean model in their browsers, they need to translate these vector fields and infinite trajectories into working graphics code.
Which is a fantastic practical challenge. Let's look at the implementation details. The first requirement for their new model is visualization. They need to draw those vector fields, the river's current we talked about, so the user can actually see the saddle point geometry on the canvas.
According to the graphics documentation provided in the sources, drawing these flow lines is highly optimized if you use the drawline function correctly.
Yes, drawline in this library is surprisingly robust. It's not just for simple straight lines. You provide the start and end coordinates by 1, y1, by 2, y2, which you will calculate based on your matrix math at each grid point. But the docs highlight several optional parameters that are perfect for vector fields.
The first one is arrow n true. If you add that parameter to your function call, the PyODIU engine automatically calculates the angles and draws a precise arrowhead at the destination coordinate. You don't have to manually draw little triangles using trigonometry. The engine handles it natively.
Furthermore, you can use the dashes parameter to stylize the flow lines, making it look more like a professional fluid dynamics diagram. You can set dashes true for a standard dash line, or you can pass a specific tuple like 30,5. This tells the rendering engine to draw a line for 30 pixels, leave a blank gap for 5 pixels, and repeat. It gives you immense control over the visual texture of the vector field.
For inspiration on how to structure the loops to draw this grid of vectors, the sources strongly recommend digging into the CMU CS Collection GitHub repository, specifically the Velocity Demo and Zombie V2 projects. Those codebases demonstrate the best practices for handling velocity vectors, applying friction, and running physics updates frame by frame within the strict MVC framework we discussed earlier.
But drawing the background vectors is the easy part. The real challenge of this new assignment is dealing with the explosive nature of the trajectory itself.
Exactly. This is the question that has been bothering me since we brought up the new matrix. If this new symmetric matrix causes Romeo and Juliet's values to shoot off to infinity, if their love literally explodes off the charts, won't the little dot representing their state just immediately fly off the edge of the screen? The canvas defaults to app.width and app.height, which is usually 400 by 400 pixels. How do you code a view for a mathematical model that goes to 1,000,000 or 1,000,000,000?
This is where we return to the fundamental philosophy of MVC design, the separation of the model and the view. The model, the actual variables app.x and app.y can grow to 1,000, 1,000,000, or infinity. The model doesn't know what a screen is. It doesn't care about pixels.
Right. It's just tracking the pure math.
But the view's entire job is to interpret those mathematical numbers and put them on a 400 by 400 grid. To do this, you must implement a coordinate mapping system. You need a function similar to the two-screen function in your original toy model that acts as a translator between math coordinates and pixel coordinates.
In the toy model, two-screen just takes the math x and adds it to app.width divided by 2, which shifts the origin from the top left corner of the window to the exact center of the screen. But that is just a linear shift. If my math x is 1,000,000, adding 200 to it still leaves it 999,000 pixels off the screen.
Exactly. So to handle an explosive model, you have two primary architectural choices. The first is dynamic scaling. You modify your two-screen function so that it divides the model values by an ever-increasing scalar before drawing them. As the numbers get larger, the view essentially zooms out, keeping the state dot visible on screen while the vector field around it scales down.
That sounds mathematically elegant, but maybe visually confusing for a simple simulation. What is the alternative?
The alternative is to accept the boundaries of your world and implement collision detection. You let the point fly, but you write logic to detect when it hits the edge of your 400 by 400 reality. The 15112 CMU graphics guide, provided in the sources, has an entire highly detailed section dedicated to collision detection math, which is perfect for this assignment.
Let's walk through that because it's a crucial skill. If the scholars want to trigger a dramatic game over state or maybe an explosion graphic when Romeo and Juliet's emotions hit the wall, they need to use these formulas inside their on-step controller.
The guide outlines two primary types of collision detection that are relevant here. The first is point circle collision. If you want to bound your simulation within a circular arena, perhaps drawing a large ring in the center of the canvas, the math relies on the Pythagorean theorem.
You just calculate the distance between the state dot and the center of the arena.
Correct. You take the difference in their x-coordinates, square it, add it to the square of the difference in their y-coordinates, and take the square root. If that distance is less than or equal to the radius of your boundary circle, the point is safely inside. The moment that distance exceeds the radius, a collision has occurred, and your controller can trigger the explosion event.
And what if they just want to use the standard rectangular edges of the canvas itself?
Then they would use the rectangle collision logic. Even though the state is drawn as a dot, you mathematically treat it as a very tiny rectangle defined by its bounding box. The logic provided in the CMU source for checking if two rectangles overlap is brilliant in its Boolean simplicity.
It really is. It avoids complex spatial algebra and just uses 4 simple logical checks. Let me see if I can articulate this. The logic states that two rectangles intersect if and only if all 4 of these conditions are true. The right edge of rectangle 1 must be further to the right than the left edge of rectangle 2. And D, the right edge of rectangle 2 must be further to the right than the left edge of rectangle 1. And E, the bottom edge of rectangle 1 must be lower than the top edge of rectangle 2. And the bottom edge of rectangle 2 must be lower than the top edge of rectangle 1.
If all 4 of those Boolean statements evaluate to true simultaneously, the shapes are overlapping.
Yeah.
By implementing these checks in your onStep function against the coordinates 0, 0 app.width and app.height, you can detect exactly the millisecond. Romeo and Juliet's spiraling emotions breach the edge of the screen.
Okay, I have one final technical concern before we wrap up. We are asking the scholars to draw dense grids of vector throw lines, calculate matrix multiplications for every point on the screen, update physics states, and run multiple Boolean collision checks on every single frame 30 times a second. Isn't this going to absolutely crush the browser? Are we going to trigger that WebAssembly blocking freeze we talked about earlier just by overloading the thread?
It is a valid concern, but this brings us full circle to the sheer processing power of PyODU. The source material explicitly addresses performance through a benchmarking test that the CMU team ran. They didn't just test simple vector fields, they pushed the engine to its limits.
What was the test?
They built a complex physics simulation containing up to 500 independently moving bouncing balls. The Python engine had to track positions, calculate independent velocities, apply gravity, and run wall collision detection for all 500 objects, while simultaneously instructing the view to draw 500 distinct circles on the canvas every single frame.
And how did the WebAssembly main thread hold up?
It handled it flawlessly. The execution took, on average, under 20 milliseconds per frame to run the complete Python update loop and the JavaScript render cycle.
Under 20 milliseconds. At 30 frames per second, you have about 33 milliseconds to do all your math and drawing before the next frame is due, so it was comfortably beating the clock.
Easily. It remained remarkably consistent, offering smooth visual animation that was vastly superior to any of the older transpilation alternatives, so rest assured, scholars. Your dense vector fields and boundary collision checks will animate perfectly smoothly. The engine is more than capable of handling the math you throw at it.
So let's take a breath and look at the summit we just climbed. Listen, Sigma scholars, you came into this deep dive with a working block of code. You are leaving with the fundamental knowledge of how to build whatever mathematical universe you want. Let's summarize the tools you now possess.
You now understand the PyDide-U engine powering your environment. You know that it is actual C Python compiled to WebAssembly running natively on your browser's main thread. You understand how it circumvents the catastrophic blocking problem using custom trace functions, intentional unthrow exceptions, and stack frame saving to yield to the browser's render cycle.
You understand the strict MVC architecture that keeps that intricate dance stable, separating your pure data model, your read-only view, and your math-altering controllers. You also understand the profound Taylor series math that powers matrix exponentiation, transforming a static 2x2 grid of local rules into a flawless geometric engine of time, capable of generating circles, saddle points, and infinite spirals without calculating the frames in between.
You've seen how a simple matrix can model a tragic romance, and how adding an imaginary number to that exact same matrix structure governs the wave oscillations of Schrödinger's equation and the quantum universe. And finally, you are fully equipped with the vector drawing techniques, coordinate mapping concepts, and collision detection logic to conquer your new, explosive Shakespearean assignment.
It is an incredible stack of knowledge. But before we let you go, we promise to leave you with one final provocative thought, pulled directly from the deepest corners of the source material. We just spent this entire deep dive blowing our minds over exponentiating matrices, using a grid of numbers as an exponent to rotate and stretch geometric space.
But the beauty of the Infinite Taylor series is that it doesn't care what you plug into it, as long as you can multiply the input by itself and add the results together. In higher mathematics, this allows for even more exotic inputs than matrices. It is mathematically proven and possible to plug a calculus operator into the polynomial. You can raise e to the power of the derivative operator itself.
Just sit with that for a second. Raising a number to the power of taking a derivative. What does that even mean physically? How do you multiply a rate of change by itself an infinite number of times, and what kind of monstrous geometry does that output into the universe? That is a mathematical rabbit hole for you to explore on your own.
It stretches the very boundaries of how we conceptualize operations and verbs in mathematics, much in the same way WebAssembly stretched the boundaries of what a web browser is capable of being.
So the next time you write on step and watch a simple orange dot move across a 400 by 400 canvas in a Chrome tab, remember the sheer, staggering scale of what is happening underneath the surface. You aren't just watching a cartoon move, you are watching a quantum-level mathematical engine, executing compiled C code natively in a browser, powered by trace exception witchcraft and infinite polynomials. You will never view a simple web animation the same way again. Good luck with the new squish and stretch model, scholars. We know you are going to crush it.